is 2025 32/029. Today I will explain the practicum that I have done. This program shows the difference between two types of algorithm complexity: linear or ON and logarithmic or O-log-N. First, there is a function called hitung linear. This function uses a loop that runs from 0 until n. Every time the loop runs, it adds 1 to a variable called hitung. So the total number of operations depends directly on n. If n is 1000, the loop runs 1000 times. If n is 1,000,000, it runs 1,000,000 times. That's why it's called linear, because it grows at the same rate as n. Next, there is a function called hitung log. This function works differently. Instead of looping through all numbers, it keeps dividing n by 2 until n becomes 1 or less. Each division is counted as one operation because the value is cut in half each time. The number of steps is much smaller. For example, if n is 1000, it only takes around 10 steps. If n is 1,000,000, it takes around 20 steps. So, even if n gets very big, the number of operations does not increase too much. In the main part of the program, we test two values, 1000 and 1,000,000. The program then shows how many operations are done by each function. For the results, we can see a big difference. The linear function increases a lot when n gets bigger, while the logarithmic function only increases a little. So the conclusion is simple. Linear algorithms are easy to understand but can be slow for large data, while logarithmic algorithms are much faster and more efficient when the input is very large. Okay, the next practicum, I will explain several proofs of big O notation in a simple way. First, we have n is in big O of n squared. The goal is to show that n does not grow faster than n squared. We look for constant c and 0 such that n is less than or equal to c times n squared. If we choose c equals 1 and 0 equals 1, then for all n greater than or equal to 1, the statement is true. For example, if n equals 10, then 10 is less than or equal to 100. So we can conclude that n is in big O of n squared. Second, we have 1/2 n times n minus 1 is in big O of n squared. First, we simplify the expression into 1/2 n squared minus 1/2 n. Then we compare the terms. The term n squared grow faster than n, so dominant terms is n squared. This means the whole function is still limited by n squared. Therefore, we can conclude that it is in big O of n squared. Third, we have 100 n plus 5 is in big O of n squared. To prove this, we change each term into the dominant term n squared. Since n is less than or equal to n squared, 100n can be written as 100n squared. Also, 5 can be written as 5n squared because 1 is less than or equal to n squared. So the function becomes less than or equal to 105n squared, this shows that it isn't big O of n squared. Fourth, we have 2n squared plus 6n plus 1 is in big O of n squared. We look at each term. The main term is n squared. The term 6n can be replaced by 6n squared, and 1 can be replaced by n squared. So the total becomes less than or equal to 9n squared. Therefore, is in big O of n squared. Finally, we have 6 times 2 power n plus 21n squared is in big O of 2 power, and here the dominant term is 2 power n because it grow much faster than n squared. For large n, we know that n squared is less than or equal to 2 power n. So 2n squared can be replaced by 2 times 2 power n. This gives us 8 times 2 power n. Therefore, the function is in big O of 2 power n. In conclusion, to prove big O, we focus on the dominant term and show that other terms are smaller or can be limited. Thank you.